I'm going to pause here for a minute to see if you have any questions, because we're going to have another step further. Yes?
Could you review from that, like step 1, where we identified E, and then step 2, etc.? Could you go back through those steps
Okay.
again?
All right. Well, when we started with Maxwell's equations, there was 4 equations that were simultaneous. They were dependent on each other, Ex and Hy simultaneous. So we needed to solve those. Whenever you do simultaneous, you combine them to reduce the number of unknowns into a higher order equation, which was second order differential equation. And in the process of differentiation, to get to the second order, obviously you lost some of your constants. So you can't ignore your first order equations. You have to go back to them and use them again. The second order differential equations, we had 6 of them. Del squared Ex, del squared Ey, del squared Ez, del squared Hx, del squared H. Now we can solve all those, but each one will produce its own constants. Right? Integration constants, that is. So you have too many unknowns. Right? So what we did is we solved 2 of them only, the Ez and Hz. All right? So we have 4 constants. And we ended up with Ez plus and Ez minus, and Hz plus and Hz minus. I guess the Hz is still on the board here, and you can see the Hz plus and Hz minus. We can live with those 4 unknowns because we can determine those from the boundary conditions at the ends of the line. At the source side, I can get the plus. At the load side, I can get the minus, because that's the reflection coefficient. All right? So we reduced our solution to Ez plus, Ez minus. Now we have those 2. How do we get the rest of the field solutions, which is the Ex, Hx, Ey, Hy? So we went back to the original 4, the first order differential equations, and we manipulated them such that we got the Hx, Hy, Ex, Ey in terms of Ez and Hc. Even with that, we saw that it's going to be too big and too complicated. All right? So we figured, let's break it down to 2 separate problems. TE modes alone and TM modes alone. And later on, we can mix those modes and we get what we call the hybrid modes. It's neither TE or TM, which is simply the mathematical solution of the 2, superposed or added to each other. So we wrote the TE solution here. The TE solution assumed that E sub z is equal to 0. And we got the solution. All right? Later on, we will do the same thing for the TM solution, where H sub z is equal to 0. We end up with, can you imagine if this expression now had both? You can see how complicated it would be. This is complicated enough. Right? And as it turns out later, that our operation in the dominant mode will be only in the TE modes. So the TM modes will not show up in the dominant region. As you will see later, the first mode is the 1-0 mode, next mode is 2-0 mode, and that's only TE. TM modes don't start until later on. The transverse magnetic modes do not start until later on, so we don't have to worry about it if we are going to work in this region. Well, obviously, there are applications where you need the TM modes, all right? And that's a further step in the analysis, right? So, like I usually say, when we crawl, we don't want to run, right? We just, do the simple things. So, this is your TE solution. TM solutions, superimpose, you get the hybrid solutions. For circle guys, it turns out that the TM modes are the ones that produce the dominant behavior, and they are the ones that we need, and we'll see that as well. We'll get to that. Waveguides, dielectric waveguides, we get to the fiber optics. There will be also a different kind of tactic on how to deal with that without complicating the math. There's always, the experience of the predecessors that told us do this, you will get the easiest solution there is. If we are solving this from scratch with no background, obviously we'll be swimming in equations, right? Did I get you a good summary? All right. Any other questions?
Sorry, just like, is it only in specific circumstances when you're solving the wave equations that you can break it up into T and TM modes and solve like that? Or?
No, it's not specific anymore.
Okay.
All right? It's a typical practice and to do that, otherwise your equations get too complicated. And usually you operate in one or the other, usually. So it makes sense to use that approach. All right, let's take a simple case of the TE10 mode, right? We said 0, 0 is not going to happen because look at here, all right? Put 0, 0. That goes 0, that goes 0. There's always a sign, right? That goes 0. So the 0, 0, you may have an H sub Z, but all the others are 0, so there's no power traveling because you need both E and H to get propagation. So the 0, 0 mode is not there, so let's look at the 1, 0 mode. The 1, 0 mode, I mean, I'll put the M is 1, so I'm going to erase the M, and the M is 0, so that's a 1, cosine 0 is 1, right? M is 1, N is 0, that goes away completely. That goes away. This one survives because you have a 1 here, and the M goes away. So you only have EY and negative HX. So the 1, 0 mode is right there on the board for you. I'm going to say TE 1, 0 mode. So I'm going to erase that and that. And the cosine of 0 is 1. The cosine of 0 is 1. Both both EY and HX are the one that exists. So over the cross section, you have EY that goes sinusoid with one lobe is EY. Right? There's no EX. So electric field is doing this. Do you have an EZ? No. Do you have an EX? No. Only one component for the electric field. And that propagates along the Z-axis. And it flips polarity, right? That's a sinusoid along the Z. So this one here is sinusoid along the Z. So if I look at it along the Z-axis, that's our Z-axis right here. It may start this way, but it's going to shrink to 0, and then flip, and then shrink to 0 again, and then flip, right? It's a sinusoid. So that's your EY. That's your electric field for the 1, 0 mode. If you want to look at it from the top, so right here is a dot and shrinks weaker, and then flips, becomes a cross, becomes stronger, becomes weaker, and then flips to a dot and becomes stronger, and so on and so forth. Right? With a Z, that's your Z-axis. If you want to picture this, that's your waveguide right here. That's your cross section. This one here is a projection this way. This one here is a projection that way. The H, you have two components. You have you have HX and HZ. Right? So you have an HX and HZ. So the HX is going to be like that, and it's gonna get weaker and weaker vertically, because it goes again as sine here. I'm not gonna develop the whole thing right now, but eventually what you will have is you will have loops of magnetic field like this, all right? Next time, I'll show you how to do this one here a little bit more in details. I have a couple of minutes which I need for something else before we close, so I'm going to show you the magnetic field like I said next time. We need a volunteer to continue with the recording, because Sarah is not going to be able to continue this recording, and I think some of you are watching those and find it useful. So if any of you would be willing to take on this difficult task, being the producer, or not the producer, just the recorder, the camera person. There are other people that take care of the processing of the video and uploading later on. You do that? Appreciate it very much. So if you don't mind, spend a couple of minutes with Sarah to learn about the camera after the lecture. All right. It's not that difficult. If I can do it, any of you guys, young generation, are good with buttons and menus and all these kind of things. I'm still struggling. I can only use one. All right. Any questions before we go? Okay. Well, I'll see you Wednesday.